what we have to do is make you the presenter, not the presenter.
Okay.
Okay, and that's what we'll do when it's time for you to show on your second podium.
Okay,
Okay,
great.
well, thank you very much, and sorry for the little bit of delay getting these computers set up.
Great. So thank you very much for introduction. Thank you very much for coming to my talk. I will talk about what our company is doing, what we're offering, and then I will a little bit more focus on things that we or our customers are doing using our technology. And so more to the end, I will give a short tech presentation where I will show you quickly how the eye tracking system works and what we can do, or what one can do with our data analysis software called DLab. So this is also basically what I will talk about today, is the DLab and SimLab environment, which enables to simulate driving, so it's a driving simulation environment, and to measure and analyze subjects' behavior to optimize the ergonomics of cars. So this is where it's widely used. The content of the presentation will be to first give you an introduction of our company and to tell you what our goals are, what our objectives are. Then I'm going to focus on the overview of our simulation, measurement, and analysis environment, and will show you a little bit more in detail what means DLab measurement and analysis environment and what means SimLab simulation environment. And then I will focus on some examples from the automotive industry that will show what our customers are doing using our technology. So these are results we are allowed to show, because most of the results we are not allowed to show because they are secrets. And point 6 is a short product demonstration, and point 7 is a quick future outlook, what we think will be the next steps in our development. Regarding our company, so we founded Ergoneers in 2005 as a spin-off from the Institute of Ergonomics from the Technical University of Munich. In the meantime, we have 25 employees and 3 locations. So that's our main office in Germany, in the north of Munich. This is in the south of Munich, where we are building the driving simulators. And this is the new office we recently opened up in Portland, which Anne is managing. So what we also try to do is to work on some committees, like the ISO committee for the evaluation of human-machine interaction. So we are not only people that are developing technology to evaluate human-machine interaction, we are also considered as experts. And so we are allowed to be in these committees to really drive the future development of these methods and technologies to measure and analyze human-machine interaction. And what we strongly do is we are working together in funded research projects with a couple of universities and research institutes, such as the Technical University of Munich. So TU always means Technical University, Kaiserslautern, Chemnitz, and University of Kassel, so that we can really work closely together with what is currently done in the research and to bring that into new methods, modules, products that we can then offer to our customers. So what is our objective? We are strongly working in the automobile or automotive industry. In the meantime, every single German automotive manufacturer is our customer. That means they are all working with our measurement and analysis technology. Many of them, in the meantime, are getting our driving simulator, and nearly all of them are using our consulting services. And what really is the objective, or the biggest problem for them, is that they have many ideas of what they can bring into their cars in the future. So when you take a look at the current market, then you have a BMW iDrive where you can interact with your car with a single knob. Then you have the Audi man-machine interface, then the Mercedes Command. You have single-turn push knobs, you have touch screens, you have adaptive cruise control, you have lane keeping assistance systems, and. So there's a variety of possibilities to bring new things into the car. And the question is always, which is the best one? or what shall we focus on and what shall we bring into serial production. And what a company cannot do is to make 10 ideas, to bring 10 ideas to serial production and then to choose the best one. But what they have to do is to make a decision as early as possible, to know which one is, or which idea is the best one, then to bring this one to serial production. And this is what we really try to help them with our tools, so that they can test ideas, concepts in a very early stage to make them, we call this feelable, touchable in a driving simulator, so that they can try out new ideas with subjects in a very early stage and then choose the best one, or check if a new idea is really worth to focus on this in the future and to bring this in a future car. I will have in one of the examples later on, I will show you an example of what Audi did. And it was a very cost-intensive, or it would have been a very cost-intensive development. Like it's called a haptic structure touchpad. And their question was, is it really worth to bring this into serial production? Or is this just a crazy idea with no advantages? And you will see how we can quickly figure out if this is better or less good than existing things. A bigger problem the automotive industry is currently facing are product liability and legal issues. So there are really recommendations from the automobile, so that's AEM, what AEM means, Automobile Alliance Manufacturers. Then YAMA is Japanese Automobile Manufacturers Association, and ESOP means European Statements of Principles. So these are our guidelines which give recommendations regarding driver distraction. That means if you bring something into your car with which the driver can interact, then this has to fulfill several requirements regarding distraction. And this is what the car manufacturers test with our software and hardware to make sure that what they bring into their cars fulfills these requirements regarding driver distraction and influence on the driving performance. And internationalization and benchmarking. So even though BMW sits in Munich, develops in Munich, tests in Munich, they're selling their cars worldwide. And what they have to make sure is that the iDrive can be easily operated in Germany, in the States, in China, in Japan, in India, in South America, everywhere. And this is why they have test facilities all around the world. And they need to ensure that no matter where they test something, that they can perfectly compare the results and bring everything together. And so we are supplying them with our measurement and analysis hardware and software, and they're using it worldwide. And in the software, we have an ISO standardized process, which guides them through the experiments and makes sure that no matter who runs the experiment, and no matter where the experiment is done, the data is always gathered in the same way and can be compared afterwards, which is really important. And what we're doing is our company is basically split into two big departments, Ergoneers Solutions and Ergoneers Consulting. On the solution side, we are developing the tools, measurement and analysis tools, so that one can really plan, measure, analyze. And we're also building up labs, from small usability labs to big driving simulator research environments. So that means this is the side where we provide the technology, and the consulting side is the one where we help our customers in applying our technology. That means if someone like Audi gets a new driving simulator research lab from us, then normally they also get a consultant from us that runs the environment, that helps them in implementing the new methods into their development process. And we can do that with in-house consulting and on-site consulting. In-house means one of our consultants comes for a month or two, does the job and then leaves. On-site means they keep our consultants for a year or two or 3 or 4, and they work constantly for them on their side, help them set up the new system, implement that into their development process, and also to run the experiment and to draw conclusions based on the result. So that's a higher level way of consulting. Yeah, that's an overview of some of our customers. So as mentioned, so this is what you can see on the left side. We're really working strongly in the automotive industry, but we're also getting into I don't know if that's the right word, the airplane industry with Cassidian, EADS, Honeywell. So they're companies that are producing airplanes or that are very deep into the airplane development process. And they, of course, also want to figure out how well their interaction design is in cockpits, and this is why they also need our technology. Then many universities and research institutes all around the world, and also companies like, maybe you know Procter & Gamble, they're using it for market research. That means how to place a product in the supermarket, how to make the packaging design, how to make the advertisement. And so they're really intensively testing all around the globe in terms of market research, how to improve their advertisement and product placement. Yeah, that was just a brief introduction to what our company does and what our objectives are. And now I'd like to give you a quick overview to our measurement and analysis environment. What is in the center of all the activities is our software called DLab. That's a process software which supports the whole experimental process, from planning to measuring the data to analyzing the data. And so DLab is the center framework, and to DLab one can connect several sensors, such as eye tracking, video observation, audio measurement, physiology, any kind of data stream you can send to our computer, which is normally driving dynamics data from a car, speed, distance to other cars. And we can also synchronize with motion capturing systems to really capture synchronously where someone is looking at and what is he, for example, doing with his hands or with his body. And that again plays well together with our driving simulator environment we call SimLab. And there we call them smart simulators. That means mock-ups or cars equipped with a screen or with a 360-degree projection where we can simulate driving. And that is again synced with our DLab environment so that we can measure synchronously what happens at the steering wheel while someone is looking at a screen and doing something. And thereby our customers can really precisely figure out the influence of new systems they bring into the car on the subject's behavior. So these are some examples of applications we have. So as already mentioned, we call it transportation science is one of our biggest applications, but also market research, education, behavioral science, design clinics, control rooms, factory planning, biomechanics boards. These are all potential applications. An emerging one is virtual environments. That's an example from a customer which is using our eye tracking system in a virtual cave to test the design of bifocal lenses. So their biggest issue is how to make the transition between far and near. And that has a huge influence on how comfortable you are with these glasses. And so this is what you can see based on these boundaries, and always when it's shortly becoming black, they can already simulate the bifocal lenses in the virtual environment. And what they can now figure out is what's the influence of how the bifocal lenses are made on their customers' gaze behavior and on how comfortable they feel with these different layouts. And so therefore one has to wear our glasses and also shutter glasses to get a 3D impression of the environment. And we can tell exactly based on the crosshair where someone is looking at, and based on that they can figure out the influence of their bifocal lenses and optimize it until the subjects show a more or less natural behavior. That's an application in virtual environments. Let me show you also something in transportation science. So this is how it looks like when someone is entering the destination into a navigation system. So he's driving in a driving simulator. then that's the screen where he has to enter the information. And then we can measure whenever he's looking at the screen. And based on these glances towards the screen, we can calculate the driver distraction. And then imagine you have two different screen layouts. We can easily tell afterwards which one was less distractive, which one had less influence on the driving performance, and simply which one was better. Okay, let's just, okay, it doesn't work. So, also quite interesting, let me show you that quickly, is design of a car. So that was a quite interesting study for Mercedes-Benz in Germany. So their Mercedes CLS is kind of a design icon for them, and they wanted to improve the design with the next generation. And they had some ideas what they could do, or some design elements they wanted to have on the car to make the design even better. And our job was to figure out, do these design elements work? Do they really attract the attention, or are they just useless or senseless? And it was interesting to do this study and to figure out if potential customers really look at these design elements, and then to give that back to the designers so that they know if their ideas work or not. And the study was really very successful and very helpful for them. And they also showed it on Mercedes-Benz TV, which was shown here all over Mercedes and all of their factories around the globe. And let me give you a quick idea of how our DLab looks like. So here you can see someone wearing our glasses. So these are the eye tracking glasses. You wear them on your head. They are capturing where you're looking at. You can also walk around. So there are no restriction in the freedom of movement. Then the crosshair, of course, shows you where someone is looking at. You can draw those areas of interest, and our software calculates where the subject is looking at. Then this is how it looks like when further videos are captured, like what's the face expression of the subject, what is the subject doing with the hands, what's the forward view, what's going on a display in the car. Like this is how it looks like when driving dynamics data is measured and then plotted afterwards, so that one can see how, for example, speed or distance to the car ahead changes over time. And what our DLab measurement and analysis environment is basically doing, it records synchronously all these possible data streams. They are synced to each other, then one can open them in DLab, replay them synchronously, and mutually analyze all the data. And later on I will give you some idea of how that looks like with a project I have on my computer here. I can show you how DLab looks like and how the synchronous replay and so on works. Just some words regarding our simulation environment. So what we do is we break down a simulation environment into 3 parts: the mockup, the site simulation, and the simulation software. Mockup means where you really sit in. We have a self-developed mockup which looks like that. The advantage is that everything is very flexible and one can freely arrange displays and input devices and thereby quickly test new concepts. But we can also, of course, connect a real car to the driving simulation. Therefore, we have to measure steering wheel angle and the inputs at gas pedal and braking pedal, and thereby we can connect also a real car to our driving simulation. Then the second part is the site simulation. So our customers can choose between just a single screen for the forward view simulation up to a full 360 degrees around site simulation, which is then very immersive. And what is really important is also the simulation software, where we have 3 levels from essential to enterprise. Essential means one can get only the parts which are necessary for driving and kind of a scenario library. With professional, our customers can really design their own road networks, their own scenarios. And with enterprise, that's really the one which is for developers and researchers. There one can design own control algorithms for driver assistance systems, or also connect own hardware to make hardware in the loop simulation. So this is really then a development and testing tool. Let me give you some examples how our driving simulators look like. So that's a very small one, which you saw in the picture already. So this is, in this example, what our customer Fujitsu is using. They are implementing new concepts and ideas they have and show them on exhibitions to have kind of an interactive environment. This is at a university in Germany. They have a 360-degree surround simulation with a BMW 6 Series convertible. So that's the forward view, that's the rear view. This is extremely immersive. That's something in between with a 180-degree forward view simulation with our mock-up and 3 screens for the rear view simulation where you can see the rear view. And these are just some more examples of delivered solutions. So let's get more into examples from the automotive industry. Well, our customers, that's an overview of the applications where our customers in the automotive industry are using our technology. It's really intensively used to test new driver information systems, to figure out how well the driver can interact with these information systems while driving. And that's basically measuring the distraction and the influence on the driving performance. Then to test new driver assistance systems, such as an adaptive cruise control, lane keeping assistant, head-up display, collision avoidance systems. Then driver behavior, to figure out how someone behaves in different situations and which problems drivers have, to develop assistance systems based on the knowledge of drivers' behavior. So if you know that drivers have a certain problem in intersections, then you can figure out what technology might we develop and bring into the car so that we can assist them to better cross intersections. Then it's perceived quality and design. This is what you saw with the Mercedes CLS example, with the design elements. And also human modeling and motion capturing. These are examples like ingress and egress, trunk loading, where you measure the body posture and try to optimize the geometry of the car so that you don't get called bad body postures. So one big topic, as mentioned, is driver information systems. Typical questions are, what is the distraction? What is the influence on driver performance? Can you operate the devices blindly, for example? Can it be interrupted? Because quite often you have to stop interacting because the driving situation is getting more complex and more demanding. AEM compliance means, does the information system fulfill the requirements from the Alliance of Automobile Manufacturers regarding driver distraction? And of course, a big topic is benchmarking. So BMW, of course, wants to know, is Audi maybe better or not? And if yes, why and where and what shall we do? So benchmarking is a big topic. And modules which are typically used to do that is driving simulation, driving performance measurement, eye tracking, and things like activity analysis based on the recorded videos to figure out which errors are made while interacting and why, and to improve the interaction design based on the knowledge of which errors are made. So this is what I mentioned before. That was a system, or that was an idea Audi had 4 years ago. Their problem was that when they have a touchpad in the car, you can't operate it blindly because you can't feel what you're doing there. And the idea they had was to bring this braille technology, which is used for blind people, into the car. And that enables them to, so you can see all these small pins on the touchpad, and they can actively control the pins to move them up or down, and thereby represent the shape of a screen on the touchpad. So you can see all the buttons here. So this one, this one, this one, that one. They are haptically represented on the touchpad. That means when the finger moves there, you can really feel them. And when the finger is there, they are highlighted on the screen. Yeah? And the question was, how does this work compared to a normal touch screen? Is it better? Is it worse? Does it have any influence? And so what we did is we did an intensive test with 30 subjects in the driving simulator, and we compared the same tasks with the haptic touchpad with the same tasks with a normal touchpad. And when you take a look at the results, then you can easily see that with the haptically structured touchpad, the task duration is shorter, lane deviation is less, and also the glance duration towards the display where you interact is less. So that was with a and the important thing is with the prototype. We compared a prototype which was not perfect with a serial system, which was already optimized and perfect. And by getting these results, it was crystal clear that this technology has huge advantages and high potential. And what Audi did afterwards, they really focused on the development and presented the first Audi A8 prototype with a haptic structured touchpad on the CES conference in Las Vegas. And probably with the next A8, this might come into serial production. But the key is that using our technology, they were able to figure out if this has potential or not in an extremely early stage. And by knowing, yes, it has potential, they can really invest the money without having to suffer that it was for nothing. A second topic is, as mentioned, driver assistance systems. Typical questions there is the driving performance enhanced or increased? Then which design is optimal? That quite often goes into the design of the control algorithms, the interaction. Then a big issue is always the change of control. So this is what you quite often have with things like adaptive cruise control. It works quite well in 99% of the time, but suddenly it loses the car ahead, doesn't know what to do, and hands back the responsibility to the driver. And then the driver has to overtake like that in a critical situation. And to design this change of control is quite a critical thing in the design of driver assistance systems. Controllability is becoming a bigger issue. Controllability means, so 5 years ago, you only had an adaptive cruise control system in your car. Today, you have adaptive cruise control, lane keeping assistance, lane change assistance, night drive, blind spot detection, collision alert, traffic sign recognition, and. I can remember I was able to try out a prototype from a car manufacturer 5 years ago, which had all these nice gadgets on board, and I was able to drive it for an hour. And then the experimental leader asked me, what's your biggest issue now? And the only thing I thought, okay, I would like to switch them all off because they're all different. They had a different interaction concept. Everyone was helping but distracting, but all together, no way. And so we call this controllability, that you can really control all these separated assistances at a time. And this is becoming more and more of an issue because more and more of these assistance systems enter the car. And again, the modules we use is driving simulation, driving performance measurement, eye tracking, and activity analysis to figure out how well the interaction design is designed and how much of a help are these assistance systems. What I have is a nice example from a company called Continental. It's one of the major suppliers for the automobile industry, and they designed a haptic gas pedal. And via this haptic gas pedal, you can feed back information to the driver. And in Europe, a very high percentage of the cars still has manual gear shift. And a lot of fuel is wasted because people don't know when to shift or how to shift at all and so on. And what is currently entering the cars more and more is an optical gear shift indicator, which tells you shift up or shift down or shift to this and that gear, which we know is not of help because it's somewhere down here, very small in the instrumental cluster. You don't see it. But all the automobile manufacturers tell this helps to reduce fuel consumption by 2%, which is not true. And so don't pay money for it. The idea was, why not use the haptic gas pedal and use like a double click, which is already known, to inform the driver you have to do something now. And what we did is we equipped a car with, we had the ability to shift between these three possibilities. Reference condition, nothing, only optical gear shifting indication, and the combined optical and haptical gear shift indication. And then we had a course which took about an hour to drive. It was Autobahn, it was city, it was urban, everything, quite a nice mix of everything. And the question was, what's the influence? And that's just a quick result. Reference, optical, haptical, and optical. And what you can see, that's no influence, but the fuel consumption was reduced by about 8% using the haptical gear shifting indication. And so that's just the result, but we could also easily figure out why. And so we used eye tracking to really show that the optical information is not seen, and it's not seen, that's for sure, it's proved. But with the haptical gear shift indication, at the beginning, so it was quite interesting to see that at the beginning it's like a hint to look at the small display, but after a while they figured out, okay, always when cluck cluck, shift. And so they didn't even have to look at the instrumental cluster to know what they had to do. And even better, it was really like a teaching system. So after half an hour, they really started to shift already before the indication came. And so it had a very positive influence on the overall behavior. The question would really be, what is when you drive this car for a week, then the function is switched off. So will you keep that behavior and save 10% also in the future without having the assistance system? But this will be hopefully the next research we can do for them. Okay, so that was just to give you an idea of the company, to give you an idea of what we are doing for the automotive industry. And now I would like to show you really quickly how our system works and looks like, so that you can get an idea and then do a future outlook at the very end. To show it to you, Ted, I would have to somehow switch from here to here.
How do I push the full screen?
It's called Vollbild, probably. It's a German operating system.
Okay, so you should be the presenter now. You as the presenter, and what do I have to do to make
Yeah, I think we would need him. But that's no problem at all, because in the meantime,
Does he have to accept?
I don't know.
Can you escape out of that for a moment? Change. Oh, it's not right.
So maybe in the meantime, I can just tell you or explain a little bit what that is. So I'm right now wearing the eye tracking system. So it's a head-mounted eye tracking system. As you can see, I can move around, I can walk around. That's the cable version. We also have a wireless version, what means it would send the information wireless. I could even walk around in a supermarket and you would still see in real time where I'm looking at. On the head unit, there are basically two cameras. This camera is filming what I'm seeing, and this camera films my eye. And based on the calibration, we can show in this camera using a crosshair where I'm looking at. That means when hopefully you will be able to see soon what the system shows. You will see yourself like on TV, and when I look at you, a crosshair which indicates that I'm looking at you. And when I look at you, a crosshair will appear hopefully on your face. And so this is how it basically works. And then data is captured, and afterwards I would define areas of interest, like your head, and your head, and our software would or your head, and our or your head. Yeah, you have a question?
How much does it like obstruct your view, and
Mm-hmm.
do you think that you have data capture on?
That's a very good question, which is asked quite often. So the thing is, what you might realize is that there's a camera right in front of my eye. This is distracting me for about 2 or 3 minutes because I know that there is something, I'm focusing on it, but as soon as I start doing something, that disappears. It's like with you having glasses, they're also obstructing the view strongly, but so the thing is, why this does not disturb is that it's so close that you can't accommodate to it, so you can't see it sharp, and it's not moving relative to your eye. That means when you move your head, that also moves. And this is why our brain simply, after 2 or 3 minutes, blends it out, and then you don't notice it anymore. Yeah.
How do you reconcile distance in relation to the eye tracking? So how does it know how far away you are?
Mm-hmm. Yeah, so what we do is when something comes closer, it's a so-called parallax error. But that's only an issue when, so there are basically two planes we have to take into account. Closer than 80 centimeters or further away than 80 centimeters. So the reason why it's not that big of an issue is that this camera is very close to my eye. That means the angle between my eye and the camera is minimized. And if something, okay, no, but I'm not exactly.
Finally.
Thank you very much.
Sorry.
Okay, that's not calibrated yet, so this is why the crosshair is not showing the exact position. So due to this very small angle, it absolutely doesn't matter when you calibrate on like 2 meters and then look at something which is 50 meters away or only 1 meter away. You don't notice the error. Yes. No. Then you would calibrate on this distance. So it's in the meantime intensively used for also very basic psychological studies, like reading studies, or also in market research when you browse a magazine and there is somewhere in between is an advertisement hidden and you want to figure out, do your subjects see the advertisement? If yes, what are they looking at? How much time do they spend on it? And so on. So therefore it's intensively used. And so if something comes closer than 80 centimeters, we make a parallax error, but our software has the ability to have different calibration planes. And this is what we're doing then. We have a calibration plane which is on about 2 meters, then you precise from 80 centimeters to infinity, and a calibration plane which is at about 50 centimeters, then you precise between 80 centimeters and 30 centimeters, and you don't bring anything closer than that. So this is how we solve this issue.
So can I make a comment?
Yes,
So
please.
there's an industry. It's been around for 30 years of running human factors experiments and doing eye tracking. And what's interesting to me about this company, and it's amazing that in the last 5 years they could turn into a viable and very 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 well known and top of the heap company, is that they integrate many of the best practices that some of these people had. So there was a company that did per-close, and there was a company that did pupil detection, and there was another company that did spots that you can detect, and there was another company that did physiological sensing. And these guys have integrated all of these subsystems in a very fluid way so that people can do a more coherent analysis of what's going on in a much more modern way. I don't know if that's something that you would agree with, but that's what I take away from what I'm seeing.
Yeah.
We also have something Christian hasn't mentioned is we're showing the cable eye tracking unit here today, but we also have a mobile application where we have a transmitter and receiver, so our subject can walk freely anywhere up to 500 meters where we have an uninterrupted wireless connection, so that the operator can be someplace we don't even see the person out there walking around, while we can still track exactly what they're doing and what they're looking at.
Exactly. So just to give an idea of how that works. So this is the video of the eye camera filming my eye. So this is my eye now in real time. And so the crosshair indicates where it thinks the center of the pupil is. So that's the image processing of the pupil. So that's the very basic information. And then based on a calibration, see, that's where I'm now looking at. We can show in space where I'm looking at. See, now I'm looking at the screen over there. Can you see that? And now I could also glance around in the environment, and you could see in real time where I'm looking at. Yeah, interesting. I have to be careful.
And is that shadow to show us jovial versus?
Oh, it's a very sporty talk.
Is that shadow?
Yeah, it's. I got your
To
question.
show,
I
yeah.
got your question. Yeah, it's. The shadow is actually a transparent overlay of the pupil. And the idea is so this is extremely important in the automotive industry, that you can actually evaluate what you get. And a big issue when someone works with a different system is always to be sure that what you see is really true, because you could have misdetections, the calibration might not be that good. And by showing this transparent pupil, you can easily evaluate if our whole calculation image processing is true, and thereby you can perfectly evaluate what you get. This is why all the industry and researchers that need correct and valid data like our system, because it's just honest, and we show everything we can show to prove that what you get is really valid. And this is why we show this this pupil transparently overlaid. Because imagine if now the cable is getting too short. Imagine if we had a misdetection, then the crosshair would appear somewhere outside the pupil, and you would immediately know, okay, something's going wrong. I have to correct that data. And so, like, this is the data recording, and let me show you how the data analysis in DLab looks like. I just don't have access to my own desktop now. I don't know why. It does not let me access my desktop right now.
So maybe we can just explain it.
Yeah, what I
We're now running at 2:30. Some people have meetings they have to
okay.
go to, so just to, maybe there's some concluding things and maybe some
Yeah.
figure
Okay.
out where people would imagine using this that you haven't thought of, or talk about some of your partners
Yeah.
that maybe they'll find out more from.
Yeah. So what I could, when we can switch finally over here again, I could show my
And if there's any
last
more
nice slide.
and more information, I have business cards here. I can follow up with you by email and send information or answer questions as well.
Thank you. So let me, at the end, give you a future outlook. So what, as mentioned, a very important thing is that our customers can test their ideas as early as possible, because if they already have invested a year or two in developing something, that's already a lot of money which was invested. That means the earlier they can test their ideas, the more money they can save if the ideas aren't really good. Yeah. And so this is why we try to get more and more into virtual product development. And a very nice project we're doing with Audi currently is to have such a virtual mock-up, which is, it's a mix between a real and a virtual mock-up. That means you really have some parts are really physically there, but the mock-up itself doesn't look very nice. And the beauty of the car comes from the head-mounted display. That means the subject wears a head-mounted display. We show in the head-mounted display the interior of the car. So the interior comes from the CAD program, goes to the head-mounted display. We capture the head position with a motion capturing system. Thereby you can look around in your car as you would normally do. What you can see in the head-mounted display changes based on your head position, like also the environment changes when I'm looking around. And by having this closed loop, we can quickly simulate any interior of a car you have in CAD. So you can change the car like that, blue, green, yellow, in milliseconds. And so this is one thing you can...
And at Halloween time, you can put monsters in the corners and have snakes coming up through the display.
Whatever you want. So that's one thing, showing something. And the other thing is, we of course also want to measure in the virtual environment where someone is looking at, how does he behave. And therefore we bring eye tracking also in head-mounted displays. There's a short video that shows how this works. So we have the head-mounted display, we're having small cameras inside, they capture where someone is looking at, and then one can wear the head-mounted display and we can still measure where he's looking at in a virtual environment. And that means you don't need a physical prototype, you only need a virtual prototype, and we can already test a virtual prototype regarding distraction, regarding what attracts attention, and so on. And furthermore, besides that, we can also measure physical stress by measuring the body posture and apply ergonomics methods which calculate physical stress based on body posture. That means we can evaluate physical stress and gaze behavior already in virtual environments. And this brings us even closer to the very beginning of the development process and enables our customers to evaluate their designs and ideas in an extremely early stage. Okay, so this was it. Thank you very much for your attention, and please feel free to ask questions.
I know since we're running a little late, we'll just take a couple questions and then we'll move to the hall where you can get to know each other a little bit more. Gal.
Just a quick one. What about pupil diameter? Is that seen as a relevant metric, and is it measured and tracked, and what do you do with it?
It's measured. So we're measuring the size of the pupil, we're measuring height and width, because the pupil is never round, because we're looking like that and the pupil is always moving around, so it's always elliptical. And we're measuring blinks. And so these are very basic measures which are more used in terms of driver fatigue, but not in, yeah?
Yes, well, I guess I'm thinking, is if someone looks at something that seems to be attracted, does the pupil dilate or compress? And, is that seen as a measure of the emotional response, I guess, to what's being seen? Or is that too hard to
No,
tell?
that's not used for that, but there's currently quite a lot of research done in terms of mental workload, and to use the pupil diameter to make conclusions regarding mental workload. This is so we will also be working in a European funded project for air traffic controllers, and so the number of planes will increase, so also the workload for the air traffic controllers will increase, and that means if you have today 5 air traffic controllers which have to manage 5 planes at a time, this will be maybe 10 planes at a time in the future, and when the number of planes increases their ability, and you don't know that, then a catastrophe will happen. So what we try to figure out, is there a possibility to get an online workload measurement? And then if you figure out, okay, this air traffic controller is at his personal limit, switch over planes to a different one. And to be able to do that, we really will be taking the pupil diameter into account and use that as a predictor for mental workload. Welcome. Yep.
One last, hang on.
But don't throw it back to me, okay?
How does it work with lens correction? So prisms, heavy magnification that someone has to wear?
So no problem are contact lenses. That's absolutely no problem. No problem are normal glasses. We also can film through shutter glasses and polarized lenses. So that is very important in virtual environments. So they're also no problem. The only kind of glass which can be a problem are, and this might be of surprise for you, anti-reflective glasses. They can be a problem because anti-reflective means anti-reflective in the visible light, but increased reflection in the infrared spectrum. That's just a physical phenomenon. And what happens is, so we're with our head unit, with our glasses, we are enlightening the eye in the infrared spectrum with a small LED under the eye camera. And what happens when you have so we can, if you want, we can try out yours. Maybe you have one, then you can see. Yeah. Prism is not an issue, but anti-reflective is an issue. Can be an issue. And so what happens is that you get kind of a blurring on the glasses, which reduces the contrast for us. And what you have to do, and this is why this piece is flexible, so you see you can move it. You have to find an angle where this spot is not covering the pupil, and then you can continue. So yes.
So
exactly.
So I think for more detail.
So the 1 second. The only thing, it takes maybe a minute to adjust it. Yeah, but so it's good when you know about that issue, and then you can adjust the eye camera to work around it.
Well, thank you for everybody for coming. I know some people have other meetings they have to get to. We'll please take as much time as we can out in the hall. I hope your assistant will help, President, American President will help get the materials out there, but I want to make sure people have a chance to ask you questions right now in the hall. Okay, thank you, bye.
Okay, great, thank you.